Hello, everyone. Welcome to today's webinar, Architects and Engineers Unite, an Embodied Carbon Reduction Game Plan. My name is Twyla Neely-Strite, and I'm the Education and Operations Associate at Illinois Green Alliance. And today's program was put on by the Illinois Green Alliance Programs Committee, which is a volunteer group that coordinates education events covering a wide range of topics throughout the year for the green building industry. The team that organized today's event consists of Jessica Haberstock and Ben Bartel. You've all been muted upon entry, so please type any questions you have throughout the session into the Q&A using the Q&A button at the bottom of your screen, and we'll get them answered at the end. And this webinar is being recorded and will be sent out to you all in a follow-up email. So for those who are unfamiliar, Illinois Green Alliance is a membership-driven nonprofit organization that advances green buildings and sustainable communities for all. Our 5-year strategic plan pushes the green building industry to meet or get on the path to net zero. We achieve this work through education events like panels and building tours, by engaging communities and partnering with organizations across Illinois, and by advocating for new policies and legislation. You can check out our website, illinoisgreenalliance.org, to view free recordings of our past webinars, see upcoming events, and learn more about membership and find ways to get involved. So today's webinar is approved through AIA for 1 LU HSW credit and can also be logged for 1 LEED AP or LEED Green Associate CE hour. To request AIA CE credit or a personalized certificate of completion for architecture license CE reporting purposes, you can follow the QR code on your screen to complete the linked form. We'll also put that link in the chat now and at the end of the session again as well. This link is not intended for those who are interested in self-reporting CE hours for your LEED AP or LEED Green Associate credentials. We'll be sharing self-reporting instructions and a fillable certificate of completion for LEED reporting in our follow-up email to attendees next week. And here are today's AIA learning objectives. I also want to take a moment to recognize Illinois Green Alliance's sustaining sponsors who make our work possible. A special thank you to our gold level sponsors, ComEd, USGBC, and Sloan. You can make a commitment to advancing green buildings in communities across the state by visiting illinoisgreenalliance.org or .org/sponsorship to start a conversation about sponsor partnership today. So today we'll be hearing from 2 great speakers, Jessica and Kelly. Jessica Haberstock is an associate within T.Y. Lin Buildings. She received her master's in civil engineering from Columbia University and her bachelor's in architectural engineering from the University of Kansas. Her professional experience includes private and public institutions and ranges from new construction to historic preservation, renovations, and existing building assessments. As the building sustainability leader, Jessica works to expand sustainability practices, develop education materials, and keep the firm on track towards the SE 2050 commitment of achieving net zero embodied carbon structural systems by 2050. She's currently a member of Illinois Green Alliance's Programs Committee. Kelly Moynihan is a principal at Nurture, a design leader pursuing the preservation, celebration, and innovation of carbon-free, equitable, high-performance projects with experience in affordable housing, single and multifamily residential, K-12 higher education, civic, historic preservation, adaptive reuse, and interiors. Kelly's a certified passive house consultant, Living Future accredited, well-accredited professional, and a LEED Green Associate committed to decarbonization through creating beautiful, healthy places for all beings. Kelly is involved as the AIA Chicago Board of Directors President-elect, AIA Chicago COAT 2030 Commitment Knowledge Community Co-Chair, FIAS Alliance Chicago Board of Directors, and an active member with Illinois Green Alliance. Using the design process as a guide, today Kelly and Jessica will be discussing a realistic, intentional, integrated approach to designing for embodied carbon reductions. They'll highlight practical and timely opportunities to reduce embodied carbon, particularly in areas where architecture and structural engineering are interconnected. Through the design process of a project, They'll dive into embodied carbon benchmarks and the health, economic, social, and governance impacts and benefits to the client and the project. After we hear from our speakers, we'll have an audience Q&A led by me. So remember to add your questions to the Q&A throughout the program so that our speakers can address them at the end. And so now I'm going to pass it over to Jessica and Kelly to get us started.
All right. Hello, everyone. We'll go ahead and jump in. As Twyla said, my name is Jessica Haberstock. Just a quick intro to the firm I work for, T by Lin. I work within our buildings group. We're structural engineers who really strive to practice joy with meaning and have a collaborative spirit. We work on a wide range of projects, as you can see on the right. About half of that is new construction and half of that is existing buildings. We love to work on preservation, adaptive reuse, sustainability, as well as some other niche groups like lightweight structures. I will pass it over to Kelly.
All right, good afternoon, everybody. Thanks for sharing your lunch hour with us. I'm Kelly Moynihan. I'm principal at Nurture Architects. We're a architecture firm here in Chicago, 100% woman-owned, woman-led, and just certified, which is a corporate transparency program through Living Future. Our firm specializes in mainly the nexus between historic preservation or in loving old buildings or existing buildings, and partnering that with sustainability, high performance technology to help revitalize those to find new life in their communities. And so listed here are just sort of our kind of ethos and how we approach projects. But we really combine building science and technology with our love for buildings and where they came from and telling their stories from the past and into the future.
All right, so we're just going to dive into some quick definitions just to make sure that we're all on the same page as we move through the next slides. So embodied carbon is the sum of greenhouse gas emissions released during the life cycle of the material. So that goes from the material extraction through manufacturing, building it, using it, and then at the end of life, disposing it. Operational carbon is the sum of carbon used during the building operations. And global warming potential is the unit that we use to quantify that carbon. A whole building life cycle assessment is taking a look at the embodied carbon of all of the materials within a building through that full life cycle. So from the extraction, building it, end of life, disposing of it. And the product stage is just looking, this is from an EPD here, just looking at raw material extraction, bringing it to manufacture and manufacturing that product. And environmental product declarations, or EPDs, are the disclosures that allow us to determine the embodied carbon of a product. And then a quick, why do we care and how does this all fit into what we're all doing on a day-to-day basis? So many of us, I'm sure, have signed on to AA 2030 and or SE 2050. And these signatory programs, of which Kelly and I's firms are part of, are really striving to make net carbon buildings, including both embodied carbon and operational carbon, by 2050. So really they're designed to kind of link within one another in order to meet those targets, in order to ensure that we continue to have a happier planet. And with those comes a lot of accountability and data sharing and tracking that each firm has to submit in order to comply. We'll pass it over to Kelly.
Okay, thanks, Jessica. So today, I don't believe we're going to necessarily introduce you to any brand new concepts you've never heard of. And instead, we're here to talk really about how we approach projects through a multidisciplinary approach between architects and engineers over the course of a project with the goal of reducing embodied carbon. And so I think we want to start by just saying that, acknowledging that typically, you know, a project team is formed, and maybe, you know, the typical organization structure is architect hires engineer, architect leads a design, and engineers kind of react to that design, and you wrap it all up in a nice set of construction documents, and it gets built with lots of challenges along the way, we can all acknowledge. But today we want to talk about if we could design an ideal system or method of how we would coordinate together, you know, towards a common goal, which is reducing embodied carbon, regardless of whether or not a project is charging you to do that, right? Regardless of if a client is asking for it, you know, how do we approach it with that in mind from the get-go? And so I guess I just want to show this as this project timeline graphic to sort of acknowledge something that is inherently true about all projects, that when you start with a project at concept design and into schematic design, that's when you have the most design freedom or creative control. And so you'll notice on the timeline that starts high on the blue and starts to slope down as you go through a project, because as you move along, more constraints are discovered, costs come into play, realities set in, and so your choices sort of start to funnel down. Also, as a project goes on, your decision making, you know, the smarter you can be earlier, and the more exploratory you can be earlier, it impacts like what the cost implications would be in sort of like the penalties of those choices happening later. So as a project continues along this timeline into construction, if you have to react to something later because you didn't explore it, test it, think about it, research it, coordinate it, the impacts of that can be big costs, or that you have very limited options of what you're able to do. So I'm just sort of acknowledging that those are things that are just true. And I think anybody on this call who's worked on a project from beginning to end would probably agree with me. So if we go to the next slide, what we're trying to introduce is how do you imagine along that timeline how an architect and engineer work together, knowing that those things are true. And so this is sort of like imagining an ideal system, an ideal method. I acknowledge that there are lots of other factors that come into this, but let's just put those aside for today's conversation and imagine that we could work in a very collaborative, exploratory environment as we move through a project. And in that regard, the way, you know, Jessica and I see this as working together on projects, and we have worked on several projects together, that over the course of a project, the roles have to change, as far as at one moment, someone will be leading or testing or sort of engaging more in the exploratory, like what are we trying to do, versus the other is reacting, listening, responding. It doesn't mean that one is not also doing the work, also contributing, but there's sort of this pivot of who's kind of leading the charge. And if you go to the next slide, the way we're outlining this process shows that as you move through schematic design, the architect's sort of leading the conversation, and the engineer or consultant team is coming along with it. And then an inflection point happens like right about at design development. And that's sort of a moment where the targets and goals and, you know, aspirations set in those early stages have to start to translate into reality. And that's when we, the architect, have to rely on our engineers and expert consultants to start folding in those realistic elements. And then sort of the roles change. And I believe as an architect, too many times that ego is not checked at the door. And sometimes it's not about who's in the front seat versus the back seat. It's who's in the driver's seat versus who's in the passenger seat in the navigation. And so these things need to change as a project goes on, with the hope that as you move into construction documents and the actual like finalization of these things, that you meet at a certain point and you synchronize. So I don't think this is like necessarily a you know, revelatory timeline, but I think it's important to highlight that it's the way we get to better solutions is if we understand each other's roles and how they can influence the actual design decisions as a project goes on. So with that, we're going to kind of march along that timeline through a project and how those roles will change. What are the important things to be looking at those moments? And so I want to start with conceptual design and starting with an integrated mindset. So again, this isn't about who's in charge or who's leading, but instead coming together from an integrated design perspective. And that means we're thinking about the things on the top of this line over the things on the bottom of the line. So progress over perfection, transparency over excuses, the we over me, courage over fear, and action over status quo. And this is a cycle that should continue throughout the design process, but everybody needs to kind of come to the table with this attitude for this to work. So if you go to the next slide, we believe that we start all of our projects with integrated design workshops or ways to kind of facilitate that spirit or that energy at the start of a project so that we're bringing everybody to the table physically usually to start ideating on what this project could be, as well as educating one another. I mean, I'm not a structural engineer. I'm not a mechanical engineer. I know a little bit, and I certainly have my experience coordinating with those disciplines, but like I need to hear from them directly to do my job better. And so that's really like how everybody should be approaching the project at the get-go. So if you go to the next slide, this is where, as concept design starts, it typically is the architect's role to start leading that conversation. And so this is where we would test boundaries of the program. Perhaps that's something that was given to us by the client, and start to ask the questions, how can we scale back or find synergies in the uses that are already outlined? How can we push for like cultural or behavioral changes that result in space saving or energy reduction? So while these things are talking about concepts high level, they really have space implications, carbon implications, energy implications. And so you have to start by asking these questions. Also acknowledging that not everything can be a priority. You have to sort concepts and ideas into categories such as needs, wants, and wows, which are the differences between functional non-negotiables or immediate remediations that are required versus dreaming bigger outside of everybody's comfort zone and what's possible. I believe it's our job to be asking the client and all the stakeholders, what would make this a landmark project that best represents you? You'd be surprised how little people think about what that might mean for them unless they're actually asked. So really, this is where we help guide the process. We start with the conversation of what are our current assets? Where should we put most of our energy into testing and exploration versus where can we simplify or just use the fundamentals? Because time is also a big factor in this process. If we had infinite time and infinite dollars, all of our projects would be, carbon neutral. Then kind of the next stage as we start from a conservation mindset first, then we move into smart design, where we outline the decision-making moments and opportunities for optimization throughout the process. And then we think ahead. We try to future-proof as we're, designing it in concept. How do we think ahead and how we might be able to adapt or adjust to changing needs for this building, this space, this organization, whether those are seen or unforeseen? If you don't ask those questions at the beginning, it'll be too late by the end. So I think I'll just mention this. This is sort of an obvious one, but I think it's worth noting that too many times I think projects are assumed that you're going to, have a blank slate or start from new, or generally, I think people have a hard time necessarily imagining what they could use an existing asset or element or building to start with. And that, at Nurture, we do a lot of our work in existing buildings. I know Jessica at TY Lin does as well. And so it maybe doesn't apply as much to our firm, but I think if there's ever an opportunity to make a case for using existing elements, like, you should do it. It's the easiest thing you can do when it comes to embodied carbon. And so like almost offering to doing retrofit, test fits, exploring renovations, whether or not you were asked to. I just think it's an important thing to stress that this needs to come usually from the design team to even suggest that it's something that's possible. And that there are plenty of case studies and examples of where this actually was financially beneficial to do, not just from a direct cost or hard cost of construction, but also like for resale of the project, or what the actual inherent market value becomes of that project should you do a reuse instead of a tear down new construction. So then moving into schematic design, this is where, again, the architect is sort of, after listening to a lot of the things that happen in concept design and the integrated design feedback loop, that this is where we start to do our testing, and we're starting to think about the massing and orientation. what the fenestration type, sizing, spacing might be, roof geometry, you know, how does that address envelope and energy? And then this is where we start to fold in our other disciplines, right? So as we're testing these massings, this is where Jessica and her team starts to say, okay, I see what you're testing, but like we need to help test those things with you. What does that mean for a structural layout or a structural type? I think it's also important, I want to stress this too at this stage, that especially if you're working in an existing building, that the earliest you can advocate and push for exploratory demo or structural probes, you can never do it soon enough, because discovering existing conditions to work with rather than react to is really, really key when it comes to the optimization of the embodied carbon in the project. At the concept or schematic design phase, these don't have to be considered as design barriers or restrictions, but more so just a part of the equation towards the right solution. You know, our inherited conditions can help define the structural grid or the structural solution, structural system, as well as define what the spaces might be as we check that against the program at the schematic level. It's just so much easier to deal with this at this stage, but too many times I think people put this off because they think, well, we generally understand the building, or we don't need to worry about that till we define the design further. And that is the wrong mentality. The later you find something, the harder it is to incorporate it into a set design that everybody's already bought into. And now you're trying to fit that into something that everybody has already, you know, decided is the right direction. So I'm just kind of adding that in here as another thing that ideally would be happening at the schematic design at latest, hopefully early design development stage. Just want to stress as a moving on to the next slide, in schematic design, this is also when we start to think about envelope, and as a certified passive house consultant, I'd be remiss to not say we should all be thinking about our projects with building science hats on and using passive house principles, whether or not you're certifying your projects. This is where you're really exploring how you do a well-insulated, airtight envelope, again, whether that's new construction or adaptive reuse. But then how that translates into what the systems modeling is for MEP, structural, like the earlier this happens, the better. But this also helps you start to think about materiality, both of the structure, finishes, and what the weights of those things are, what the spacing of those things are going to need to be. Specifically, when it comes to insulation, which is the next slide, this is probably one of the ways that architects can influence kind of the carbon impacts of a project easiest by how you're deciding what your envelope sandwich is made out of, not just from a performance standpoint, but also like what insulation are you using, you know, again, not just for its R value qualities, but what are its global warming, you know, impacts. And so there's a lot of things we can do when we're exploring our envelope with just when we're looking at insulation. And then I think one of the last things I'll say in the schematic design phase is this is also when we should start doing modeling, both energy modeling and carbon modeling. Model early, model often should be the mantra we all bring to our project teams. There's lots of methods, tools out there. That's an entirely different presentation. I grabbed this graphic here that sort of outlines a bunch of tools that are out there. I'm not necessarily subscribing to each of these categorized in the phases that they are, but I thought it was an interesting graphic because I think what it's trying to say is that certain tools are better used at certain times in a project based on level of detail or level of sophistication of the modeling. But I think the earlier you can do this, the best, you know, the better outcomes you have. That's, again, not a new concept. But I think it's also important to note is thinking about who's going to do the modeling. I would say ideally you're having probably a third party do this when possible. That's not possible on all projects because that's a cost, et cetera. But I think it's important to say just because it can help keep the project team honest and have a more like objective lens look at the energy or carbon modeling of a project. Now, that's not to say that the other project team members, such as the engineers or the architects, should also maybe be doing their own internal schematic modeling of these things, be checking themselves. So I think it's just a reminder that we can all be educating ourselves and maybe advocating for your firms to be investing in these tools, as well as education of certain team members, so that you can be doing some of this in-house, whether it becomes the formal model or thing that's setting the actual targets for the project or not, is sort of irrelevant. If we all get better at using these tools and are folding them into our practice, the better decisions we can make along the way. So then moving along the project timeline into design development, this again, along that timeline I showed at the beginning, this is sort of when that inflection point starts to happen, where architect has sort of been leading a lot of the conversations, explorations, kind of testing the boundaries of things. This is when the engineers and other consultants start to fold in with their analysis, their expertise. But I'll just say from the architect's perspective, as we start to move into design development, the things we should be thinking about is keeping everything lightweight. Less is more. That also, and we already talked about trying to optimize or cinch the building best we can. Less square footage is better. How that impacts, what systems choices we're doing for MEP. We should be all thinking about all electric, low carbon refrigerants wherever possible. Again, not always feasible on every project, but something to be tested early. But also, as we're now starting to move into the actual thinking about what is this building made out of, how is it finished, exploring carbon storing materials, whether that's structural materials, envelope materials, insulation, or finishes. And as we're thinking about those things, we should also be looking for products that already have environmental product declarations, that are already disclosing what's in them and what their performance metrics are. The more we can be using those or asking for those, again, that helps drive the market by saying these are the types of products we want to specify in our projects. That's what's going to convince manufacturers that this is actually something that the market is demanding. So this is when we should start to be doing that research when we're thinking about what's actually going in the buildings. And the last thing I'll say before I hand it over to Jessica in design development is this is really when we start to refine our envelope and how that coordinates with the structure. So whether it's an existing building and that kind of comes with its own maybe choices versus new construction where you could kind of do anything. This, had you done all these steps I've already outlined, as well as starting to do the modeling and analysis, this is when you might start to refine or sort of zero in on what the choices are from an insulation perspective, how that's going to attach to your structure, how we're going to put openings in this building, and thinking about how big those should be, not just thinking about glass and energy through that, but also like what's the structural implications of those openings, maybe not thinking about huge spans that Jessica's going to get into. So, and then how do we translate from interior to exterior with thermal breaks and how that impacts structure, as well as the overhangs and shadings that we want to incorporate into our design when we're thinking about energy performance. All of these also tie back into embodied carbon because this is extra material, extra structural, extra superstructure, extra finishes. So this is when, we've sort of done the massing and analysis and sort of optimization of how we think this works with the program and start to really get into the building science and start to listen to our engineers.
All right. So just starting off, kind of the structural transition that Kelly had mentioned. If you take anything away, I say Kelly would probably agree as well, not just structure, but throughout the building. If you take anything away, I would love for you to take away that a reduction in material quantity is a reduction in material cost and is in turn a reduction in embodied carbon. This is kind of the theme of the rest of this DD phase that we're going to be kind of working through. And before we kind of jump into specific opportunities, also just pointing out, and Kelly mentioned this before, but we're going to go through some really specific things and just noting that not all of these things work on every single project, but it's really about finding the opportunities for the project that make sense for the use, for the space, everything that the building needs, and implementing those in a way that is effective. All right, so we are going to be looking at some more technical structural things. And for those of you who aren't structural engineers, just before you start to panic, We're really just going to look at things at a high level. We're going to talk through exactly what we need to know. And don't worry, any equations or diagrams like this, you don't need to understand the in-depth structural details of them. But let's dive into regular grids. So these are two examples of concrete flat plate constructions, concrete slab transferring to concrete columns with some concrete shear walls. Although they have two very different building forms, they're two examples of a regular grid and a non-regular grid. So on the left-hand side, what you can pretty easily see is that when we're looking at plan east-west, most of the columns are aligning with themselves. You know, you have a few here that are off, but primarily they're aligning east-west. And then we look north-south, they're doing the exact same thing. Now, what this does from a structural standpoint is allow for our moments, our shears, our deflections to be incredibly predictable. The slab is going to behave exactly how we expect it to. The forces, maximum forces, are going to be where we expect them to. And what that means is we can use a pretty consistent rebar grid. And all of these extra little lines that you see are additional rebar. And what you notice is they're kind of in the same place and there's really not a ton of them. And that's great. That means that we have been able to optimize our slab and we're not having to throw a bunch of extra rebar at it in order to make it work. On the right-hand side, we're just going to look at the bottom part because there's a lot happening on this building. But what you'll notice is here I've highlighted where all the columns are. And in plan north-south, the columns are actually aligning pretty well. But east-west, they're kind of all over the place. And what that means is our forces are not where we expect them to be. Our maximum moments, our maximum shears, and the requirements that we need to be able to transfer the slab forces to those columns are going to be very unpredictable. And what that means is you can see there's a lot more bars, which means a lot more additional rebar added to this slab, which means we're throwing a lot of additional embodied carbon in order to get the slab to function. Now, obviously, different buildings have different needs, and we should consider things like the long-term use of the building, flexibility, maybe program change when we're laying this out. But the more regular grid we can get with our structural columns, the better we can be at reducing the embodied carbon with just pure structural materials. And with that is also going to come a reduced cost of the project overall. All right, so looking at transfers. First, what is a transfer? You can see here we have 4 lines of columns, but this center left one does not continue down. This is our transfer. So whether that's a slab or a beam, we can see this is kind of a simplified structural diagram of that. We have our column supports here, where our load is just going directly into that support. Whereas at the center of this slab or beam, we have our column forces being transferred out. So that load needs to get out through the slab or beams to the columns to the right and the left. And where this can really have a big impact is when we're looking at deflection and most importantly, compound deflection. So this is all very exaggerated, but our slab or a beam is going to deflect as shown here. And with that goes our columns. And with that goes the slabs attached to that column, which means that this lower member, in order to meet the not just added load that we're adding to it, but also to ensure that this compound deflection from up above, these upper members kind of moving down with the column as it deflects, are not impacted. We're going to have to increase the amount of structural material that we're using here in order to ensure that we're meeting all of the required capacities. So a good way to easily reduce embodied carbon is to reduce, if not eliminate, the number of transfers that we have on a project. Now let's look at a case study. This is a very simplified little stick frame building made of steel. We have 4 bays that are all the same size. And in the corners, we have moment frames to act as our lateral system. We are assuming that there we have lightweight concrete on metal deck on each floor, and that we're utilizing shallow foundations at each of the column locations. So we've sized these members accordingly to meet their required capacities and deflection criteria, just using a baseline deflection criteria. And pointing out here that this is a W18 by 119 columns in the middle. At the exterior, we have W18 by 86 columns, and then all of our beams are W12 by 58. So removing that one column in the center bay at just that one location, everything else is the same. We wind up increasing our two exterior columns to W14 by 550 and increasing that transfer beam to W14 by 233. So this has increased the weight of steel in this little case study building by 62% and increased the embodied carbon by 36% of the entire project just by removing that one column. That is equivalent to adding 11 cars on the road for a full year. All right, so moving on to cantilevers. First, what is a cantilever? If we look at this building on the left here, we can see that there are these beams that are extending off of these concrete shear walls that are set back on the building. And they're unsupported. There's no column underneath them or anything. They're just extending out. That is a cantilever. And then our backspan is the member that you can't really see in the photo, but extends back beyond and has our support point. So in the structural diagram that we have on the right, this section here is our cantilever, and its length is noted in this equation as A, and our backspan is the section in between our two support points beyond that cantilever, and its length is noted as L. I'm quickly going to add in a little deflection diagram here because we don't have one. What you can see is that the typical behavior of a cantilever is that the cantilever end deflects downward and the backspan deflects up. Again, this is very exaggerated, but is the general behavior we see typically when we're looking at a cantilever condition. What I really want us to focus on here is how the length of the cantilever and the length of the backspan impact our different structural items that we need to always check. So at the base here, R represents our reaction, our max reaction, which is here, which is equivalent to our two shear forces. We have our maximum moment, which is also located at that R2 at our support point here. And then our maximum deflection, which is typically located at the end of the cantilever itself. So A being equivalent to our cantilever length, we can see that when we're looking at our reaction and shear forces, we're adding it with our backspan length in order to get the total length of the member. When we're looking at our max span, we are directly multiplying that length in order to get that max span, and then or max moment. And then when we're looking at our deflection, we are squaring it and then adding it to the total length of the max span. So you can see kind of as we move down in these equations, we have a larger and larger impact to what those numbers are going to be. The higher those numbers are, the more material we need, structurally higher section properties we need in order to meet the criteria. When we look at our length of our backspan, we can see it has a much less impact. And when we're looking at our reaction or shear forces, we can actually see we're dividing it here. So the longer that we have that backspan, the better it is for those shear forces. So if we can reduce what those cantilever lengths are when we do have them and increase the backspan, it can really mean that we can optimize our structural shapes. We don't need to add a bunch of material and section properties in order to meet that criteria. The other last thing to note is you'll see that the arrows actually change direction in the reactions, and that's because at the end of a backspan, we can also see sometimes a net tension. So if you just think about you have something cantilevering off, you push down on it, the back end wants to pop up. And what that means is that sometimes our connections where we do have that net tension can get incredibly hefty in order to make sure that we don't see the back end popping up. All right, floor buildups. So this is actually an example from one of Kelly and I's projects where we have Here we have our floor finish, we have our structure, and we have our ceiling. What's not really shown in this diagram that you typically see on most projects is what's happening in between those spaces. So might have some ductwork, might have some, other routing for electrical or plumbing. There's often a lot of things happening within these ceiling spaces. And when that space gets taken up, it can limit the amount of structure depth that we're allowed. And instead of having a lighter, more optimal structural shape, or maybe even a more optimal structural material like wood, which requires more depth, we wind up getting crunched. And we need to add a bunch of additional weight of our structural material in order to get the capacity and the deflection criteria that we need. So let's look at a quick example. Here we have 3 wide flange beams that all have the exact same section properties. They can handle almost the exact same amount of loading. On the right-hand side, we have a W18 by 35. So it's about 18 inches in depth. And that 35 is the pounds per foot that that section weighs. So as we reduce 6 inches, we go to a W12 by 45. We are increasing the weight by 28% from that W18, but also increasing the embodied carbon by the same percentage. And when we reduce that even further to W8, we're now at 58 pounds per foot, which is a 65% increase in weight and a 65% increase in embodied carbon. So, W18 is not going to work on all projects, but maybe instead of going for a W8, we leave room for a W12. And we kind of see that place of compromise that is making sure we're not adding extra embodied carbon from the get-go. Another way we can really optimize our structural materials is using each material the way that it operates best. And what I mean by that is concrete, for example, works great in compression, terrible in tension. Steel is really good at long spans. Masonry is very good at arching and compression. So taking a look at each of those individual materials and deciding when to use each one in the way that it works best is going to allow us to make the most efficient structure that we have. Obviously, with that comes making sure that the cost side of things or maybe adding a whole new trade to a project makes sense. But the example we have here is a very small one. We had a mostly wood building with some steel added in where needed. And we were using, very hefty 3 floor ply wood members for this long span. And we looked at what would it take to replace that really hefty wood member with a steel member. And when we did that, we actually found that although we increased the steel embodied carbon by 2.8%, we decreased the wood embodied carbon by 23% and decreased the total embodied carbon on the project by 2%. Again, this is a really small example, and in general, this project was a small one. But if you take that logic and you apply it to a much larger project or to multiple areas on a project or to our projects altogether, we can really start to see that reduction overall. And then looking at, there are some high embodied carbon materials that we can look to substitute when it makes sense. The biggest culprit in any structural system is concrete, and of that is lightweight concrete. In order to make lightweight concrete, they take regular aggregate that they would use in normal weight concrete. They heat it up to a really high temperature, it expands, and it becomes lighter. That takes a significant amount of energy, such that lightweight concrete has almost double the embodied carbon to normal weight concrete. Now, there are reasons why we use lightweight concrete. And one of those biggest has to do with fireproofing. And you can see on the left-hand side here, there's a diagram of what the change in thickness requirements are in order to meet fire rating assemblies. So making sure that when we're switching from lightweight to normal weight, we have the room to grow our floor assembly. But also knowing that we're also adding weight to the project. And so making sure that the foundations don't have a huge impact when we're making that switch. The other is making space in the same way we talked about horizontal structure, making space for vertical structure. The HSSs have nearly double the embodied carbon that a wide flange shape does. that HSSs are more efficient in the amount of material that they use. So it's not really a 1-to-1 ratio, but allowing for space for columns can mean that when it makes sense, we can utilize a wide flange that does have a more reduced weight and a reduced embodied carbon where it makes sense. Back to that case study, we're going to focus in on switching all of our lightweight concrete to normal weight concrete. Everything else is the same. Our transfer column is back where it was. And what we see is as we've increased the weight of the concrete, we've gone from a W18 by 119 to a W18 by 130 in our columns. So we've seen overall on the project an increase of 4% in steel, but a reduction of 6% of embodied carbon throughout the entire building, which is equivalent to taking 2 cars off of the road for a full year. All right, pass it back over to Kelly.
Thanks, Jessica. And I think she's just highlighted why it's so important to have your engineers weigh in on this stuff, because while she just showed you a lot of very, technical diagrams and calculations, that is how you arrive at some of these very important decision-making moments when it comes to the structure and how that then impacts the architecture, not just from a spatial layout per se, like if the grid changes, but also experientially, like if the overhead beams have to get deeper, what do we have to consider from how we're going to finish that out or fireproof it, or what the head height's going to be. So like, it's just so important that that analysis is done in design development with your engineers, but again, like sort of letting them lead that part of the process, because that's where a lot of this science comes into play, and then how you can actually move forward into now construction documents, where we move on to refining those details, as well as doing some final carbon modeling based on all of those decisions made to date, and verifying that that's what's actually now being executed in those contract documents for construction. This is also when we start to finalize our specifications. I mentioned in design development, that's when we start researching and starting to make those decisions, but this is when we really actually finalize that and realize how much power we have in our specifications when it comes to the impacts on embodied carbon in our projects. So if we move ahead to the next slide, this is also when we're starting to detail really down to, the fine details of the project, and really thinking about how we might design this, not just from a materiality standpoint, but how we might think about it in its future life, designing for disassembly or deconstruction. Again, not always feasible on every project, but maybe parts of it is, maybe parts of the interior are. And so as you're making decisions on, finishes or layout, I'm thinking about what kind of resilient materials we can use that would possibly have a second life. Are they modular? Can they be, accessed the way they're mounted with the types of connections that you're using? So thinking about bolts and screws versus welds to steel, like can this thing come apart easier and have a future life? Using things that are more standardized versus specialized or custom, so that again, they could be reimagined for something new. And thinking about how it would be dismantled. Like, are you designing the assembly in a way that a person's hand could actually get in there and take it apart? Or would the whole thing just sort of go to waste if this building ever needed to come down? Also, this is when we can think about dimensions down to like 1/4 of an inch when we're thinking about no cut, no waste. So thinking about, say, the interior dimensions of a room or a space and how that might relate to the proposed finish module dimensions, or thinking about the exterior assembly layout or opening placement and adjusting it as needed, even just, an inch here, 1/4 inch there, to thinking about how's that sheathing going to panelize? How's that jip going to panelize based on how it comes off the truck? You'd be surprised that like when you do the analysis of like making those small adjustments, when thinking about no cut, no waste, inches or fractions of inches can have huge impacts when it comes to waste, and then obviously the overall embodied carbon story of the project. And then I think as we move into thinking about specifications, what we try to think about when we're picking things is avoiding over design. Less is indeed more. You don't need to have 18 different things to enclose a room. How can we simplify down to maybe raw materials, or thinking about where they come from, local or regional materials, rather than shipping them from, overseas? how are we using salvage materials? As well as, as we think about our specifications, rather than sort of leaving open specs or sort of up to interpretation for the general contractor to then just go pick whatever's cheapest, we should really be defining those from their performance qualities, and using performance or prescriptive specifications, because so much work has been done to this point. In the way we actually have a control point on that in construction is how we write our specifications. And also just thinking about manufacturer advocacy again, if we're demanding these things or thinking about low embodied carbon materials or, disclosure of what's in your materials as we're thinking about our specifications and doing outreach to manufacturers, like that's also what helps better materials to come to market.
Just kind of continuing off of what Kelly was saying about specifications. And I'm going to breeze through these because this slide on its own could be a whole 60-minute presentation. But when it comes to concrete, kind of echoing what Kelly said, a formative concrete specification is really the best way. And that is allowing the ready mix plant to work with different alternatives that previously haven't always been something they can do, which may include alternative cements, maybe reducing changing the water cement ratio, different things like that can help them meet a certain benchmark of embodied carbon for their concrete. Structural engineers can also look for where it maybe makes sense to have a longer cure time, particularly at different structural elements where having the formwork up for a little longer doesn't have a big impact on the construction schedule, such as foundations. And optimizing strength, instead of using 6,000 psi concrete everywhere, maybe it makes sense that these shear walls need the 6,000 psi, but the slabs only need 3,500. And that can really help reduce the embodied carbon overall of the concrete. With steel, we can specify that requiring electric arc furnaces. You can see on the bottom right-hand side here that electric arc furnace process has at least over half of the embodied carbon as a traditional process. We can also look, when we have really heavy members, at using ASTM A913, which is a higher yield than like an A992. With wood, we can require certain certifications such as FSC or SFI. We can also look at using advanced framing, which really optimizes the amount of wood material we're using by aligning our structural members, and also help a lot with that operational carbon side of things. And utilizing prefabricated materials, whether that's modular construction or precast panels or SIPs, because these are all made in a controlled environment, there's a high level of quality control. So there's not a bunch of added members or increased strength that you need because you know kind of what you're getting. And it also can have a much reduced waste of the material itself. And looking at the finishes and facades during CDs is the time we're really defining exactly what we're using. And we really want to take a look at how the length of our member ties into our deflection equation. So whether this is looking at the floor finishes like a plaster or a tile that has a high deflection criteria, or a facade element like stone, or we see a lot of these window systems or these foldable partitions that also have really high deflection criteria in order for them to operate. What we can see is over here we have a diagram for just a simply supported beam with a uniform load on it. And our L is our length. And in our equation for deflection, we are taking L to the 4th power. So as that length increases, it's not a linear equation for the impact on deflection. It means in order to meet the same deflection criteria, we have to add significant structural section, aka structural material, in order to meet that criteria. So something to consider when we do have kind of those higher finishes, or we're looking at what exactly we're specifying, and we're coordinating with the architect to understand the impact of that. And having a regular grid, kind of going back to previous topic, can also really help with this deflection issue because it changes our equation a bit that we can utilize.
And I know we're short on time, so we'll run through this last piece quick. So now we're in the final phase of a project or construction administration, which again, if you think about that curve, this is when our creative control is at its lowest. And it's also when we're usually welcoming a new person onto the team, which is the general contractor and their subcontractors. Ideally, they could have been along for the ride earlier, but that doesn't always happen. And so we have to think of them as a new team member and not an opponent to this process. A lot of times there's battles in the field over this is how you do things versus this is how we drew things. And instead we should be engaging them as soon as we can. But if that starts with, a pre-construction meeting where we sort of highlight what the sustainability requirements and sort of outline all of this work that's been done to date to try and get that collective buy-in and understanding why it's important to the project. We should also be highlighting what specifications are really going to be important to pay attention to and what the tracking policies are going to be. And just, again, reiterating what the requirements and goals into that kickoff meeting. And really coming at this with as construction goes on, there's always things that come up, unforeseen conditions, situations, costs, et cetera. And having, being willing to come to the table ready to compromise or adjust or react to the realities of construction. Certainly using everything that's been done to date, the research, the testing, the analysis, but understanding that we're going to probably have to get, be nimble and creative in the field quickly. And again, so it's keeping that spirit alive of integrated design throughout construction is very important.
And then last is using EPPs to kind of verify everything we've been talking about. We've made a lot of assumptions. We wrote these specifications, and we've analyzed what the embodied carbon is on a project. And now is the time to check that everything we've assumed is what is actually being built. Knowing that sometimes things change during construction, or this material is being used instead of that material. This is a good way to make sure that we're still hitting those benchmarks or the embodied carbon targets that we set at the beginning of a project. And that may require updating that life cycle assessment in order to make sure that we're where we're supposed to be.
I think we'll just end on this slide reiterating this timeline and what I'd like to call the architect to engineer curve to success when thinking about embodied carbon. So we've tried to highlight today, kind of as you march along a project, what the opportunities or things you should be focused on at different stages of design, when someone's leading versus when someone's listening, and when those inflection points happen in the process. And the hope is, as we outlined on the last slide, that with the curve of the synchronization, that the embodied carbon targets and performance also starts to slope down if you're doing all these things. Obviously, this isn't an ideal world. There are lots of other outside factors that contribute to this, but if we're coming to projects with this in mind, that I believe that this is the best, recipe for success when it comes to reducing embodied carbon in a project. And I think the last thing I'll leave everybody with is that, we all come to a project with our expertise and, our backgrounds, and we certainly are all very well qualified to be there. But I think what's important is to check your egos at the door when we're thinking about embodied carbon. Instead, come with 3 different E's, which is, again, your expertise, but more importantly, your empathy and excitement for doing what's good. Because if we're not doing it, no one's going to be pushing for it. And I think that's where we will wrap up with 1 minute.
Thank you, Jessica and Kelly. Yeah, everyone, I know we've got to 1 o'clock here, and we have a lot of questions. I'm gonna ask a question from our list from the audience, but I'm also gonna ask our speakers to hopefully answer some of these offline for us, and I can try to send some responses out to you all afterwards. But I have 2 upvotes on 1 question from the audience, so I'm gonna ask that one. That question is, for slabs and columns, is there a better use case for captured carbon injection between these different structural features? And they gave as an example a carbon cure.
Yeah, so just for folks who aren't familiar, carbon cure, or there's some other proprietary products, are basically someone's captured carbon and they inject it into the concrete, which therefore means that there's a reduced embodied carbon because you've captured something that was through some sort of manufacturing process. And really, the point of Carbon Cure and its similar products is that it should be able to be used in any application. Essentially, once a ready mix plant has it added to their line, it could be added to any concrete mix. So there shouldn't really need to be a limitation on where it's used.
And I'll ask one other question kind of on the other side of things. Somebody said, regarding concrete and specifying things to reduce the embodied carbon, what do I need to say to my engineer for them to consider that? Especially when we're getting into things like frost protected slabs and maybe other atypical installations. Seems like we're getting at like, what is the communication that's
Yeah.
needed?
There are some requirements in ACI, like frost protection. There's certain, if you have certain exposure categories that you can't make certain changes that I kind of talked about. But there are still a lot of opportunities with cement alternatives. I'll also maybe quickly in the chat send, there's SE 2050 has some really great resources on specifications and structural materials. That is a great kind of intro to how to start with adjusting your structural specification. So that could also be a really good place to start.
Okay, I'll ask one last question. We have from Katie. When considering modular products, what are the drivers for specification? Lead time or local sourcing?
Ooh, that's a tough one. I think it depends. I think lead time is always going to be a factor when you're confirming what materials are going in the project, but usually that's what comes later when a contractor's on board and sort of saying like, I see you specified this, but it's going to be 20 weeks to get that. And so sometimes that then requires us to pivot and look for something else. So I don't know that lead time, we always know what lead times are when we're looking at products. However, that's always probably a good question to be asking as you're researching your products, because if it's going to have a lower lead time, like that's always going to be more ideal. But when we're thinking about it from an embodied carbon standpoint, if you're asking me which one matters more, it's probably going to be locally sourced. You know, the closer it comes to the site, like that's better for the embodied carbon story. So I don't think that's a good answer to the question, but I think a lot of times we don't have control on the lead times of things. But that's why it's also good to maybe have some alternates, or like when you're listing them in your specifications, like you're thinking about, here's something that's more local versus maybe something I found out has a lower lead time, and it might be decided in real time because those things also change. But I would say most often something that's coming closer is also probably going to have a lower lead time usually, but that's a big asterisk on that.
And the last thing I would just add is when we're talking about anything modular, anything prefabricated, the earlier you know about that, the earlier maybe you can advocate for a contractor be on board, because they're the ones who can connect with, you know, the potential subs who would be doing that work and get a better idea of what we're talking about. So maybe we can plan ahead, and maybe those modular pieces, we actually push the deadline up a little on those so they can get started and it doesn't wind up impacting the schedule of the project.
Yep.
Thank you both. I don't want to eat into everyone's 1 o'clock meetings too much. So we're going to end here, but I will send our speakers that questions list and hopefully we can get a few more answered off screen for you all. And those can be sent out in our follow-up email, which will also include a recording of this and a PDF of the slides. And I'm also going to throw in the link one last time, our feedback survey link. If anyone has the time to answer a very quick, like 6-question survey, we would love to hear your thoughts on today's webinar so that we can keep improving our sessions. Thank you, Jessica and Kelly, for joining us today. Thank you for sharing with our audience, and thank you all for attending and listening. Hope you all have a good day.
Thank you, everyone.
Thanks.
Have a good afternoon.
Bye.